Hello and welcome to another session of classical motion of a single particle. So, in this session we will solve two interesting problems of classical mechanics using the method which we just discussed, that is the Lagrange's equation of first kind. So, if you remember that Lagrange's equation of first kind is given by this one, this equation, that is for a particle of mass m, the m r double dot, which is the mass times the acceleration, minus the force which is excluding the constraint force. So, this is only the force where the particle is subject to, and this is not the force related to some contact or some tension or some response of any medium or material. So, this is the force field in which the particle is subject to move, and this excludes any type of constraint force, plus lambda times gradient of phi is equal to 0, where lambda is the undetermined multiplier of Lagrange and phi is the holonomic constraint which we consider here. So, phi is a holonomic constraint. So, we can start with a very simple case where a particle is moving in a circular orbit. So, now you see our approach will be to identify the constraint. So, in a circular orbit, if I say the particle is moving, a particle is moving in, let us say, xz plane. So, let us say like this, I can take this as the x direction, this is the z direction. I say a particle which is at P, so this is the origin O, and the particle is moving in a circle, let us say in the anti-clockwise direction. Then you can always say that, so this is x and this is z, and if this is the polar angle theta and this is r, then of course x is equal to r cos theta and z is equal to r sin theta, that we all know. Now, coming back to the problem. So, in this problem first I can write, so m, I have a motion in 2D and that is my choice, that is not a constraint actually, that is the choice. You can say that the motion is on 2D, but then the constraint is that now the particle has to move in a circle of radius, let us say small r. So, I can now say that this small r is a constant. So, m x, I can actually write this thing in this way. So, m r double dot minus f I plus lambda. Now, first we will attack this phi. So, what is the constraint here? The constraint is x square plus y square will be equal to r square, which is constant. So, phi will be equal to x square plus y square minus r square, and that is equal to 0. So, I just write this x square plus y square minus r square, that is equal to 0. Now, here I am just telling that it is just moving in a plane, and for this type of motion you just see that there is, I am not saying that any force is acting other than the force of constraint, for example. So, I do not know that is there any force field, because when I am saying that a particle is hanging vertically in the case of pendulum, I know there is G is acting, but here when a particle is just moving in a circle, I can simply say okay, maybe the motion is only due to the force of constraints, and this type of force is actually not present. So, I can actually say this is not present. So, this is 0. Okay. Using Cartesian coordinates, I can actually write then m x double dot, okay, plus lambda. So, here also I have to take the x component, which will be 2 lambda x, okay, is equal to 0, and so I should not put like this, and m z double dot plus I think I have made a mistake over here. So, instead of writing z, I have written y everywhere. I will simply change that to z. Yes, okay, yeah, and here as well. Okay. So, you will see, and m z double dot, okay, will simply be plus lambda 2 lambda z is equal to 0. Okay. So, now you will have an equation which are two equations which are quite similar. Okay. So, now you can see that we have to eliminate lambda to find a relation between x and z. Okay. And now for that what we will do, this is also pretty easy to do. So, I just use this thing that x is r cos theta and z is r sin theta, and r is a constant here. So, only variable is theta. Okay. So, I can use this. So, x is r cos theta, that means x dot is equal to minus r sin theta, theta dot, okay, and then x double dot will be equal to minus r cos theta, theta dot square, and then there will be minus r sin theta, theta double dot. Okay. Similarly, for z, I know r sin theta, z is equal to, so z dot will simply be equal to r cos theta, theta dot, and then z double dot will be equal to minus r sin theta, theta dot square, plus r cos theta, theta double dot. Okay. So, now you just put these things over here. So, what I write in green now. So, in green I will have these two equations, actually these two, okay, but in polar coordinates. Okay. So, r is a constant for our system, that is the constraint. Okay. So, I can write then m times, okay, m times minus r cos theta, theta dot square, minus r sin theta, theta double dot, okay, plus 2 lambda, x is r cos theta, okay, cos theta, and that will be equal to 0. Okay. I have also from this equation, this z equation, I have m minus r sin theta, theta dot square, plus r cos theta, theta double dot, okay. Then I will have plus 2 lambda r sin theta, which is equal to 0. Okay. What I can now do, I can just multiply this equation by cos theta. I can multiply this equation by sin theta. Okay. If I do and then I just subtract the first one from this second one, what I will have, you will see that I will have m minus r sin theta cos theta theta dot square here, and here I will have minus m r cos theta sin theta theta dot square. So, they will cancel each other. Again I will have here plus 2 lambda r cos theta sin theta, here I will have plus 2 lambda r sin theta cos theta. So, they will again cancel each other. The only term which will be remaining is this thing. So, I will have then r cos square theta theta double dot minus r sin square theta theta double dot, that will be equal to 0 if you just do this. Okay. And then you will actually have r, so cos square theta plus sin square theta times theta double dot equal to 0, and finally you will have this is 1, this is constant which is non-zero, finally you will have theta double dot equal to 0. So, you see that means that theta dot is constant. Okay. So, this is exactly what is expected from a pure circular orbit or pure circular motion. So, you see I even do not know what actually which force is causing the motion in a circle. I just know that there is no force other than the force of constraints, and since the force of constraints are prohibited here in this Lagrange's equation of first kind, I did not mention about them. Then I started and finally I get this equation. Okay. So, theta dot equal to constant. And now of course, from that you can solve for theta, which will be a linear function of time. I will now do the usual example of a simple pendulum, but with always the fixed length. Okay. So, the simple pendulum is having a mass m, but now it is moving actually in a arc of a circle of length L, and this is the fixed length of the string, and the weight is working vertically downwards. So, I am again defining this is my x axis and this is my z direction. So, this is actually negative z direction, negative z direction. Okay. So, if I do that, then the Lagrange, so for a simple pendulum, with fixed length of the string, we have again m r double dot plus, now here I know that I have some constant force which is tension and everything, I know, I do not want to talk about them. The only force field to which the particle is subject to move is the g field. Okay. This is the Earth's gravitational field and the force is mg, but in the downward sense. Okay. So, I will write that m r double dot plus mg. Okay. So, you just remember here I just made there is a minus sign. So, here of course, you can actually write right from the beginning the minus sign, there is no problem with that, and then you write plus lambda, and this is the gradient times the constraint of this. Okay. Again here the constraint is exactly the same as that of a particle moving in a circle, x square plus z square is equal to L square, which is a constant. Okay. So, you will have the same form here, x square plus y square minus L square. Okay. The only thing you will have is that for along x direction, you will have along x direction, you will have m x double dot is equal to minus 2 lambda x, because along x direction there is no force field acting to which the particle is subject to move. Okay. But along z direction, along negative z direction, you have a force field, and that is why you actually write then mz double dot, and this becomes then plus sign, because g is acting vertically downward. So, along minus z direction. Okay. So, I will write plus mg is equal to minus 2 lambda z. Okay. I already have found how to handle this type of problem, and actually, so we simply again cast this Cartesian coordinates in the plane polar coordinate system. So, here we will simply write, you see that x is equal to, I can just simply say that this is an angle theta. Okay. So, x can be given by L sin theta, and z is given by L cos theta, because if this is L and this is the angle theta, so then this is L sin theta and this is L cos theta. Now, one thing we have to take proper caution, that is z by definition is negative in this downward direction. That is why we will write this minus L cos theta, because if you just say L is just a positive number which is the radial distance, and if you define also theta to be positive in the anti-clockwise direction, okay, measured from this vertical direction, then you can actually write this is minus L cos theta. Okay. This is something, just a convention to make sure that z is negative. Okay. You can also redefine your angle theta from this direction actually, and from there you can actually also have the same situation. Okay. Just try that as well. If you have x is equal to L sin theta and z is equal to minus L cos theta, then your x dot will simply be L cos theta, theta dot, and your x double dot will simply be minus L sin theta, theta dot square, plus L cos theta, theta double dot. Okay. Then you will also have y dot is equal to, then you will also have z dot is equal to minus L. So, cos theta is minus sin theta, theta dot, which is L sin theta, theta dot, and then z double dot will be simply equal to L cos theta, theta dot square, plus L sin theta, theta double dot. Okay. Now, we will write the equation of Lagrange of the first kind for this system in the plane polar coordinate system, and I use this green ink again. So, m times the whole thing, m times this thing, okay, and I can say that minus L sin theta, theta dot square, plus L cos theta, theta double dot, minus L sin theta, theta dot square, plus L cos theta, theta double dot, okay, is equal to minus 2 lambda x. So, if you remember this equation. Okay. So, x is L sin theta, L sin theta. Okay. I can actually write just like this, plus this equal to 0. Okay. Yeah. What will be the equation for z? Okay. M z double dot. So, z double dot is this thing, m, okay, L cos theta, theta dot square, plus L sin theta, theta double dot. Okay. So, both the terms they have the plus sign. Then you have here mg, that is the difference between the x direction and the z direction, and you will have 2 lambda L cos theta, okay, is equal to 0. Now, here again it should be minus. So, I just write because your z is minus L cos theta by convention. Okay. So, now what you will do, you will simply multiply cos theta with this whole thing. So, cos theta you multiply, okay. Here you multiply sin theta with the whole thing and then you add them up. If you add them up, then you again see that the first term will go away with this term. Okay. So, it will be minus m l sin theta cos theta theta dot square, here it will be plus m l sin theta cos theta theta dot square. Again if you just take, so this is actually multiplied with the whole thing, the same here. Okay. So, this term with the Lagrange multiplier will also go away because it will be 2 lambda L sin theta cos theta with plus sign, and here it will be 2 lambda L cos theta sin theta with minus sign. So, finally, you will have L cos square theta plus sin square theta. So, here you see here this term gives L cos theta times cos theta. So, cos square theta theta dot theta double dot, and here you will have L sin square theta theta double dot plus mg sin theta is equal to 0, and then you can write L theta double dot plus mg, sorry there is an m which is missing. So, here I should write m for both, yeah, and here I will get rid of the m. Then I can simply say this is g sin theta is equal to 0, and then again for theta tending to 0, I will have, we have theta sin theta is theta, okay, tending to theta, and the equation of motion is given by theta double dot plus g by L theta is equal to 0. Okay. So, what is this? This is again the equation of dynamics of a simple pendulum, where the angle theta is very small, and that is the popular form where you can see that the simple pendulum is actually performing a simple harmonic oscillation, okay, under the assumption that theta is tending to 0. So, you see even using this Lagrange's equation of first kind, the same technique that we do not talk at all about any force of constraint, we have not mentioned anything about the tension T, we just use the geometrical constraint itself, that is x square plus z square is equal to L square, which is a constant. Using that we finally, okay, found the equation of dynamics, and once you have equation of dynamics you can simply solve the equation for theta and theta dot. Okay. So, in this way we can solve many interesting simple problems in the framework of Newtonian mechanics, and actually you will understand that many problems in Newtonian mechanics where the constraint forces are complex in nature and you even do not know how to account for them, this type of method is super useful. Okay. And one such problem I will give you, that is the concerning the motion of a particle which is now moving downward an inclined plane. You will be supposed to solve that using this Lagrange's equation of first kind in the assignment. Okay. Thank you very much.